Hi, I am Tzvi, an NEC Corporate VP and the General Manager of our Israeli Research Labs. NEC is a multinational headquartered in Japan with a tradition of over 120 years of research excellence, starting with our founder, who worked at the Thomas Alva Edison Labs at the time. We present here a collaboration of our labs and the RISC-V solutions company, eFabless. In modern systems handling private or sensitive information, there is a continuous concern that commercial black box hardware and software may have cyber weaknesses that will be exposed in the future, compromising mission-critical designs. 2 years ago, we at NEC realized the new open source-based processors can help implement transparent security solutions in IoT and edge devices. The concept got a further boost when during 2019, news articles claimed server hardware used by the world's largest corporations has been intentionally compromised at the hardware level, and hackers have shown how easy it is to add tiny components to existing motherboards and compromise them. Furthermore, even secure designs like the Intel SGX and the Siemens programmable logic controllers have been found to have serious security flaws. This is not due to incompetence. Cryptographic security mandates perfect integration of any hardware, software, and protocol elements. And even if the components are fine, a single mistake in their application can and has created loopholes. Such events lead high security users to look for solutions which are simpler to inspect, modify, and produce for themselves. This is analogous to the move to open, hardened Linux distribution over proprietary commercial operating systems. Privacy-preserving computing means you can perform complex operations on data while the data itself remains encrypted. You can verify credentials, perform biometric authentication, or even recognize words in audio without decrypting the original data. It can be implemented in hardware using trusted execution environments such as Intel SGX and ARM Trustzone. A software-based method promoted by, for example, Microsoft and IBM is called homomorphic encryption. Yet another software method called Secure Multi-Party Computation, or SMPC, has been researched by NEC for almost a decade. SMPC's uniqueness lies in the fact it does not rely on public key infrastructure. This means the IoT device is not required to support PKI and the heavy involved computations and silicon. Furthermore, the code and protocol running on the device in SMPC are small and easy to follow and inspect. We therefore decided to try and implement an SMPC software stack on a tiny and completely open source processor, so that the vendor could download and inspect or modify the hardware and the software, and third-party security reviews can continuously be accomplished. Thus, we offload most of the security and complexity burden to the cloud, while the code on the device is minimal and can be inspected by a reviewer within a single day. To accomplish this, we needed a RISC-V based ASIC. We soon learned that actually most RISC-V implementations are not open source. Rather, just use the open source RISC-V instruction set. So we contacted eFabless from California, who will be joining us in this presentation. Based on our requests, they modified their basic design by adding memory and other circuitry. Their CTO, Mohammed Qassem, will present their path and recent collaboration with Google's Open Titan initiative in the second part of this talk. We consider the Open Titan initiative, launched much later in 2019, as further vindication of the need for a pure open source IoT security solution. In our proof of concept, we implemented the core components of the required functionality: private key device authentication based on AES, audio sampling, and SMPC shared generation. For reference, we also implemented PKI to benchmark performance and memory requirements. The sample application is therefore privacy-preserving speech recognition based on SMPC in the public cloud. Unlike the current services of Siri, Alexa, Google Assistant, and others, in this use model, your voice recordings are never in the hands of a single entity. The speech recognition is performed on the audio, which is cryptographically distributed between servers. For the detailed description of the POC, I will now transfer to Maya Cohen-Maimon, our team leader for this project.
The first POC component is AES authentication, which was done with Raven Basic Board. Authentication, or in this context, identification or signature, is a process of confirming the user is who or what is stated. Chip encrypts data with the stored identity key. The key is symmetric. The requester also has it. On the right image, we see how Raspberry Pi have authentication request verified by the Raven processor externally. Raspberry Pi source sends identity request command, which is 128 bits. The input will be encrypted with the identity key, and the Raspberry Pi can validate the results. This shows how we can add on-chip security with simplest RISC-V chips. Raven chip could have been placed on the same board with the source IoT chip. Some performance number on basic Raven. Assume we are doing authentication over 128-bit block. Performance is 15 milliseconds, 2000 slower compared to Intel i7. Even this is enough for IoT security functionality. IoT device will identify on specific occasions. IoT has lower resources and power consumption. Ravana performance will be much better. Second group of POCs is voice privacy. We have enabled audio sampling with microphone and have extracted the samples with AD connector. Imagine a simple IoT device that records your voice in your house. To keep privacy, we do not send records to the cloud, only SMPC random shares. The recording is done on chip in 8 kHz. Random shares are easily created format, extracted with AD connector. These shares are sent to 3 different MPC servers. The servers compute the heavy computation with the received random data only. 2 POCs were done for voice. On both, no recordings are sent to the clouds, only random numbers. In the first example, we have run an AI network that recognizes when you speak, private voice detection. The second POC had privately recognized basic keywords. We can use the keyword to say when we wish to send commands to the cloud. Again, we have computed the AI networks on the random numbers only. As we have shown, generating SMPC shares can be simple enough even for small edge devices. What basically is done is representing any number with 3 numbers, 2 random numbers, and the third number is a function of the input and the 2 others. Let us see as an example. If our input is 21 and we have 2 random numbers, 10 and 12, the third number can be -1, as 10 plus 12 plus -1 is our input 21. The 3 shares, 10, 12, -1, are sent to 3 servers on the cloud, probably owned by different authorities. This is very secure. Even 2 servers are hacked, the numbers are random. The servers exchange messages and compute any algorithm, like AI network, on a distributed manner. It's important to say that the cryptographic part is very small, only 350 lines and less than 3 bytes RAM. This is our advantage over other methods. The last component of the POC is the PKI implementation. We have shown Diffie-Hellman, which established a shared secret key over an insecure channel. A major step of PKI that each side will compute private and public keys. We have used the latest eFabless chips, Ravenna, for this computation. The best performance we had is 128 bits in 60 seconds, less than 100 bytes of RAM. This is very useful. Some pros and cons on our VLSI experience. Pros, it is possible to implement any program using C. We managed to run complicated architectures in impressive performances. It was easy to read and write from Flash, and it doesn't require much pre-installations if you have the right instructions. It was very easy also to use hardware. Everything was well documented. The UART, analog I/O, and so on. The open source code is more secure. The infrastructure is open and documented. Hardware can be reviewed as well. On the other side, low-level C programming has its limitation. It requires strong understanding of memory usage, usually without external library dependencies. Currently, there is no IDE, thus debugging can be a long process. We had also some issues with software old versions, some casting issue, and compiling and virtual environments.
Hi, my name is Mohammed Qasim, the co-founder and CTO of eFabless Corporation. And I would like to talk today about our experience in designing and fabricating an open source, complete open source VLSI SoC that is serving the purpose of privacy through transparency. One of the main conditions we always look at it for security and privacy is that all the software and hardware included in an SoC must be an open source, must be concise, must be inspectable. And that allows the starting point that is transparent and trusted in a way that is, you can build on it, the components all the way to the software with confidence, knowing that there is no black boxes or any hidden functions. Now, at NEC Fabless, we have created different types of SoC designs at different stages with different levels of open source content. One of the main questions here at NEC Fabless was actually how to create a market-relevant SoC design that is serving the purpose of privacy, while we have components of the design, like the foundry information as well as the IP in a proprietary form. And in order to strike that balance, what we started with is that we worked on obfuscating the proprietary IP in a way that is abstracted and allows someone to integrate it in the SoC. And the focus of the proprietary IP had to be on the interfaces and the macros, where there's no processing, there's no activity that is allowed to be programmable. So you start also from trusted components, specifically some of the analog peripherals, etc. Now, at this point, when we design it, we create the merger in-house and ourselves, and we ensure that it is consistent with the root of trust concepts. Now, the next part of that was how do we actually build the design using a design automation system. So that's also another component. But by having a completely proprietary design flow, it serves as a black box, which also comes in a way of creating a trusted SoC. So we at Fabless decided that we are going to use a complete front to back and end-to-end SoC design flow that has completely dependent on constructed from open source EDA components, different engine, and we assembled different engines, different pieces from idea all the way to GDS in a way that is compatible with the foundry process to enable us to get to the SoC. The challenge here in general is that are these flows mature? Are these engines capable of designing something that is robust and can be reusable, or maybe targeting the performance that is required? And the answer is, after investigating that and looking at it, if you're understanding exactly what the limitations are and what the tools are capable of, you can decide where you navigate where to use the tools exactly in a way that is 100% predictable and producing the performance that you are looking for the application you are designing for. So if we do it in a vertical way and we focus on these vertical applications, the design automation flow can be delivered in a way that is robust for these given applications. Of course, we had to do one or two experiments of silicon calibration to ensure that we have the predictability as well as the performance and consistency with what we wanted initially. By doing mainly if we feel that the tools are not covering everything that is expected, we add design margins and we replace some or put some guidelines around the best practices for the design. And by choosing the design flow to be vertically constructed around a certain application, we are able to, using design best practices and applying design margins in right quantities, then we're able to produce a predictable design. And based on using the open source design automation flow, as well as target the performance that we are looking for by designing the flow as well to be a part of the picture for creating that design. The last part that was challenging here is that then to build an SoC, there's a variety of skill sets and experiences that exist in multiple places. We in eFabless, our model is based on a community and open innovation. So in a sense, we enable people to collaborate across the globe to transparently and efficiently to provide the different expertise level and deliver them within one SoC or one design while sharing the expertise from analog to digital to software, hardware components. Back to the IP obfuscation or the data obfuscation, I wanted to dive here one more level and give you an example here on the slide from the left to in the middle picture. These are two representations of the same component. One of them is abstracted for the data ADC, and the other one on next to it is the original layout that is coming from the IP provider. And in this case, the abstraction's purposes is that the IP provider, after working with them, chose to keep the IP in this case for that purpose hidden and used as is in the function that is intended to. Now on the right side of the slide, you'll see that the top picture is the abstracted representation of the SoC, and as you integrate the SoC, the components are treated as trusted black boxes, except for the main component, which is the Pico SoC, the digital CPU plus everything related to the processing within the SoC. And this SoC is considered hybrid, and it is built using a combination of the open source components, as I mentioned, and proprietary components. And it's a RISC-V based design. The main open components in it is the CPU and its interface to the rest of the peripherals, as well as some of the digital peripherals, including the GPIO and the communication interfaces. Well, that has a limitation. It's still hybrid. There are still black boxes, and there are points that would still be vulnerable to misuse or misunderstanding using because it's blocked, because it's completely covered. We at eFabless, we developed a family of SoCs that are completely constructed from that technology. They are based on RISC-V with different combinations of libraries and performance levels. The purpose for that is that we wanted to initially have a diverse set of experiments so that we can, as I mentioned earlier, we can calibrate the flow and ensure that the entire process is predictable and meets our performance. This was a partnership, and it's still ongoing, between eFabless, Google, Skywater Foundry, and it's based on one of the major projects that are for the open source design automation. It's called Open Road in the US. And by doing that, it was a starting point for the laying the infrastructure for everything to be transparent. And this is just the start. We are moving forward with adding more peripherals and then building more interfaces using the PDK. Now, once they have the PDK, you have the ability to construct the interfaces and communications and Ethernet files, etc. All of the above using components that are transparent, which creates, again, becomes one deeper level in the root of trust.
To summarize, we have shown in this proof of concept that high-level privacy-preserving compute is possible with complete use of open source hardware and software design. We have also learned that RISC-V does not necessarily mean open. Most workable products are neither open nor free, and we had to search for the right one to enable our end goal. Also, we have seen that the open source development tools, while they have evolved a lot over the last few years, still pose continued challenges in functionality and consistency through the development process. Finally, in order to complete the kind of applications we are aiming for, there is a need for an open source based Ethernet IP stack, both on the physical layer and in the software layer. and we understand that that is part of OpenPython, so we intend to use it when it becomes available. Thank you very much.